This presentation is recorded to provide methodology and additional result analysis for the RGMA lab talk in the breakout session of extremes and impacts. The title is Long-Term Statistical Relationship of Hail and Tornado with Mesoscale Convective System. This study, we use two sets of data. The first is the hazards report obtained from the NCEI. Here we only consider hailstorm more than 1 inch and the tornado greater than enhanced Fujita scale of 0. The other data set is the MCS data set, which is developed at PNNL. To detect and track MCS, 3 layers of data are required. First is the upper level cloud brightness temperature, which is used to define the cloud boundary. The second is on the surface precipitation. And the last one is the 3D radar reflectivity, which is used to depict the intensity and structure of the convection. In brief, a system needs to last more than 6 hours, contains convective feature and large precipitation feature to be defined as an MCS. All the hazards report are mapped to the grid of the MCS dataset, and they are categorized into the MCS related, non-MCS related, and other. For the first category, they are generated by the large, long-lived system. And for the non-MCS related, they are generated by the smaller, short-lived, isolated system that fail the MCS criteria. And for the category of others, they are produced by the smallest transient system that cannot be captured by the early radar image. All the hazard events associated with convective core are further divided into the morphology of cellular, nonlinear, and linear, using the major axis length and axis ratio. You can refer to the flowchart for how we classify those categories. After we separate the different hazards to the MCS related and non-MCS related, these figures show their spatial distribution. Here, for the first column is the total count of the hail, second is MCS related, and third is for the non-MCS related. And the different rows represent different seasons. Apparently, winter has a minimum hail count, spring has a maximum with a core in the SGP. In the summer, the SGP core shifted to northward to the NGP, and in the fall, the hail count decreased drastically with scattered distribution across the entire domain. Regarding the MCS versus non-MCS fraction, majority of the hail are MCS related nationwide. However, the central US is more MCS related, but the East is more non-MCS related. Then let's look at the tornado distribution. Clearly, there are 2 tornado alleys represented. One is the traditional tornado alley, the other is the Dixie alley. And the tornado alley dominates the spring and summer, whereas the Dixie alley is more prominent in winter and fall. Regarding the MCS versus non-MCS component, MCS-related events are dominant in all seasons and all regions. However, the eastern part still has a higher non-MCS fraction than the central. The hazard distribution shows strong regionality, which may result from the different driving mechanism for the hazard-producing convection. Apparently, central US is more driven by the explicit synoptic forcing. However, in the east part, it's more thermal driven and affected by the land-sea circulation. Therefore, we further separate the study domain into the central and the east by using the 85-degree meridian. In this histogram figure, hail is on the left, tornado is on the right. They are separated into different severity bins according to the hail size and the tornado scale. While the dark color represents the central and the light color represents the east. First, let's look at the bars. Both types of hazard over both regions all show fewer occurrence at higher severity, which follow the common sense. We also see more events in the central compared to the east, but there are less extreme events in the east. Then the MCS fraction at each bin is calculated and shown using the green lines. Here we found that the more severe the hazard is, the more likely it's generated by the MCS. Lastly, we examine the hazard-producing convective object among different morphologies. The upper panel for hail, the lower is for tornado, the left column is for MCS, and the right for the non-MCS. Apparently, MCS has even distribution among the cellular, nonlinear, and linear. But for non-MCS, it's dominated by the cellular shape. Here is a recap of the conclusions, and thank you for your time.